All right, so let's talk about question 7 from section 1.1. So this one, we are given a situation, and from that we are supposed to provide a graph for what a position time graph for this diver. So let's read through the situation. So a diver leaps from a 3-meter springboard. His feet leave the board at time t equals 0, and he reaches a maximum height of 4.5 at t equals 1.1 seconds. So we'll start marking off the time axis. So at 1.1 seconds, I reach my maximum height of 4.5. So that should give us a little bit of a clue about what our scale is going to be. So he enters the water at t equals 2.45. So about here. Once in the water, the diver coasts to the bottom of the pool, 3.5 meters deep, touches the bottom at time equals 7, rests for a second, and then pushes off the bottom. From there, he coasts to the surface and takes his first breath at 13 seconds. Okay, so basically, I can break this journey up into steps. One important thing that I haven't seen yet, I have a guess, but I want to know what, like, if we talk about position, we have to know, like, in reference to what. So part A, let S of t denote the function that gives the height of the diver's feet above the water. Okay, so it sounds like the surface of the water is going to be, S equals 0. That's going to be our 0 position. So everything is in reference to that, which is confirmed by this in the parentheses. Note that the height at the bottom of the pool is negative 3.5 meters. All right, so we have to provide our own vertical scale. So let's think about what is the minimum height we're going to have and what's the maximum height. I think the maximum height is going to be 4.5, and the minimum height is going to be 3.5. So I don't think we can quite get away with using like 1 for all these dark black hash marks, because that's not going to let us reach our maximum 4.5. How about if we do 1.5 for each hash mark? So this will be 1.5, 3, 4.5, and then going to 0, negative 1.5, negative 3, negative 4.5. So this should at least allow us to kind of represent everything we have. So let's talk about some key points here. So he leaves a 3-meter springboard at time equals 0. So at t equals 0, my height is 3 meters. Then I reach a maximum height of 4.5 at 1.1 seconds. So 1.1 seconds, that's about here. So basically, I am just populating these points kind of based on the information I'm given, one by one. Okay, so that's it. What happens at 2 point? Okay, he enters the water at 2.45 seconds. So we said the surface of the water is height 0. What else do we know? The diver coasts to the bottom of the pool and touches the bottom at t equals 7 seconds. So at t equals 7, we have a minimum of 3.5. So about here. Okay, let's go back. Are there any other points I need to worry about? Rest for 1 second. So that tells me that at time equals 8, he's still down there, right? So I think this little section here, I could have a horizontal line. All right, what happens from there? Rest for 1 second and then pushes off the bottom. From there, he coasts to the surface and takes his breath at time equals 13 seconds. So what happens at 13 seconds? That's when he comes back to the surface. So I have a lot of points now, and I think from here, I can connect them. So it's going to sound silly, maybe, that I'm bringing this up, but he's not going to just rapidly change position. Like, he's not going to teleport or anything like that. So I have to have a smooth curve. That's basically, I'm not allowed to lift my pencil while I'm doing this. So starting from a height of 3 meters, I jump up to 4.5 meters, and then I enter the water at 2.45 seconds. Kind of missed the point, but that's okay. And then I know I want to get to the bottom of the pool at this time, rest there for a bit, and then coast back to the surface at 13 seconds when this graph ends. So I think this incorporates all the information that we were given. You have a little bit of leeway with how this graph goes, but not as much as some of the other graphs we've talked about. But hopefully this makes sense. Let's move on to part B. So based on your graph in part A, what is the average velocity of the diver between 2.45 and 7 seconds? So we've done a lot of average velocity calculations so far. Before we go back to our last slide and visit the graph, how do we find average velocity? Well, that's going to come from our change in position. So what is our position at 7 seconds minus our position at 2.45 seconds? And divide that by the change in time here. So our change in time is going to be 4.55 seconds. So let's go back and look at what those positions are. So at 7 seconds, we were at the bottom of the pool. So that is negative 3.5 meters. At 2.45, we were at the surface of the water. So that is 0 meters. So we have negative 3.5 meters over 4.55 seconds. Let's go ahead and calculate that. 3.5 divided by 4.55 is negative 0.769, and our unit should be meters per second. So this is our average velocity over that time span. So that's the calculation they wanted. They're also asking, is his average velocity the same on every time interval? So let's go back and look at the graph. So let's bracket the things we're looking at. We're looking from time equals 2.45 to time equals 7 seconds. Is the average velocity the same everywhere in there? Based on the graph that we drew, I do not think we can say that because let's say I drew a really tiny interval around 2.45 and 3.5 seconds. The way I drew this graph, this is, the slopes in here are going to be a little steeper. Another way to think about that is, since we're talking about average rate of change, their change in position from 2.5 or 2.45 to 3.45, we'll say, is more than it would be between 6 and 7. So, and the reason I chose those two intervals, they're both exactly 1 second long. So the only way they would have the same average rate of change is if they had the same change in height, which they don't. But let's look at the description of the question again. Once in the water, the diver coasts to the bottom of the pool. I don't know if they're trying to suggest there that means that I go to the bottom of the pool, out the bottom of the pool at a constant rate, but I don't think that's a given. So depending on how you interpreted that, and there is room for interpretation there, I don't think I would say that their average velocity is the same on any interval you've made between 2.45 and 7. The only way that would be true is if they had a constant rate of change. If his speed was the same throughout that stretch of time. So moving on to part C. All right, so let's talk about what we're being asked in part C. So part C is similar in some sense to part A, but now instead of trying to build a position versus time graph, we are trying to build an instantaneous velocity graph. So let's think about how to do that. So we know that velocity and position are related in some way, and that's essentially what this question is trying to get us to. So let's rely on the things that we did for part A. So when we're talking about instantaneous rate of change or instantaneous velocity, and we're looking at a graph, one thing we can think about is, slopes of tangent lines. So I have a position graph. We can think about the slopes of tangent lines here. One place that I usually like to start, and this is kind of a personal preference thing, it's not where you have to start, is looking at where your instantaneous rates of change or where your slopes of tangent lines are going to be zero. And so what does it mean to have a slope of zero, or what does that look like on a graph? What that's going to look like is we're going to have horizontals. So we're going to have horizontal tangents. So I think I'm going to have one here where I reach a maximum. So that's 1.1 seconds. I'm going to have another at t equals 7, actually for all t values between 7 and 8 seconds, because he stays at rest on the bottom of the pool. So what I'm going to do first is mark those points on my velocity graph. So at 1.1 seconds, I'm going to have a velocity of 0. All throughout between time equals 7 and time equals 8, I'm going to have a velocity of 0. So it's a good start knowing where our velocities are 0. So let's go a little deeper. Let's see if we can figure out where our velocities are going to be positive. So if we go back to our position graph, what does it mean for us to have positive instantaneous velocity or positive instantaneous rate of change? So we can think about this in terms of slopes of tangent lines again, slopes of tangent lines. Think about where these slopes are going to be positive. So as we read from left to right, where are they going to be going upward? So I believe that's going to be at the outset, because we have a positive slope of a tangent line here, or also because this diver is jumping upward. So his position is changing. It is increasing. It is getting more positive. It's getting greater. So I believe from time equals 0 to 1.1, and we can start like demarcating these. I know that between 0 and 1.1, I'm going to have positive slopes. Is there anywhere else I'm going to have positive slopes? So basically, I am looking for where are my tangent lines going to be as I read them from left to right? Where are they going to be going upward? I believe that's going to happen from time equals 8 to time equals 13, because that's after he pushes off the bottom of the pool and to go upward. So I'm going to mark that as well. So do another vertical dashed line. So from time equals 8 to time equals 13, I believe I also have positive slopes. So then it should make sense that everywhere between 1.1 and 7, I should have negative slopes. So let's go back to our graph and make sure that that's the case. So at time equals 1.1, I reach a maximum, and then it starts going downward. So hits the surface of the water at 2.45 seconds, hits the bottom of the pool at time equals 7. So I believe from time equals 1.1 to 7, I should have negative velocities. So I think we have a very good idea now as to what the signs of our slopes are going to be, what the signs of our velocities are going to be. Are they going to be positive, are they going to be negative, or are they going to be 0? So now let's try to get a sense of what these values are. So let's start at the beginning. Let's go back to our graph, our position graph. At time equals 0, I have, kind of scribbled a tangent line in here at the beginning. And it seems like as, at the very beginning here, if I were to draw a straight line to represent that tangent, it looks like I'm going upward 2 squares, which represents a change in height of 1.5 meters, and it's going right by 1 square, which represents a change in time of 1 second. I believe I can estimate that at time 0, the velocity is 1.5 meters per second. I believe I can say something similar for what's happening, as his speed starts to decrease, as his velocity starts to decrease, and he starts to head towards the surface of the water. So from there, he hits the surface of the water at 2.45 seconds. I'm going to estimate a change or instantaneous velocity of -1.5. From those, I'm going to build out my scale. So I know my velocity is going to be measured in units of meters per second. I'm going to give each of these black hash marks, these are going to represent a change of a half a meter per second. So going as high as 1.5 and as low as -1.5. So starting from +1.5 at time equals 0, at time equals 2.45, I'm going to have a minimum velocity of -1.5. And I know that at time equals 1.1, where'd my point go? At time equals 1.1, I want to have a velocity of 0. So from here, even though the velocity is still negative, so let's revisit something. If we go back to our position graph at 2.45 seconds, this is where I'm seeing the steepest downward slope. So because of that, that should be where we see our lowest negative velocity, like the negative velocity that's furthest from 0. But what happens to the velocity from that point on? If we go back to our position graph, the velocities are still negative, but they're getting shallower and shallower. They're getting less negative. So what's that going to look like on our velocity graph? Well, they're still going to be negative, but they're going to be less severe. They're going to be less significant. And we also know that by the time we get to time equals 7 seconds, our velocity must be 0. So this is a very key idea to kind of point out with the relationship between velocity graphs and position graphs is that let's just let's talk about the first 1.1 seconds here. We said in the first 1.1 seconds, the velocity is positive. So what does that mean? If the velocity is positive, what does that say about position? Well, that means that the position is increasing, which our graph shows. Position's increasing because we have an upward slope. And on the velocity graph, we have positive numbers between time equals 0 and time equals 1.1. Similarly, what does it mean to have position decreasing on a position graph? We have negative slopes of tangent lines. And if we look at an instantaneous velocity graph, we have negative numbers between time equals 1.1 and time equals 7 seconds. And then what if we're right in the middle? What does a 0 velocity correspond to? That corresponds to horizontal line segments like we have between t equals 7 and t equals 8. So a lot of key relationships here that very subtle, very important. We'll get more used to them kind of as we kind of wrestle with derivatives and what they mean. So finally, what happens between t equals 8 and t equals 12? Well, we said that our velocity was going to increase, or sorry, position is going to increase from t equals 8 to t equals 13, which means that our velocity needs to be positive. So why am I drawing a line that is, why am I drawing a velocity that's not only positive but increasing? Well, let's go back to our position graph. If we look at these tangent lines that I drew in here, every tangent line I would draw between t equals 8 and t equals 13, they're all positive, but as I move from left to right, they're getting steeper. The slopes are getting greater. So that is why I am graphing basically a velocity that's positive everywhere, but also growing. So again, a lot of subtle ideas here. If we need to talk about these things in more detail one-on-one, definitely reach out to me. This is a very, very important idea in Calculus 1. But it's also it's a little hard to get used to. So let's talk about it if we need to. So part D, is there a connection between the two graphs that you can describe? Well, while we were going through C, we talked a lot about this. So maybe it'd be best right here if I can kind of sum things up. So let's make a little table. So what things we talk about? We talked about position. And we talked about instantaneous velocity. So let's talk about some ideas and how they're related. If your position is increasing, what does that mean about your instantaneous velocity? So let's go back to our graphs here. Let's find places on my position graph where we had increases. So that's two places. That's from t equals 0 to t equals 1.1, and from t equals 8 to t equals 13. So those are increasing position. What did that look like on an instantaneous velocity graph? That's where our velocity was not necessarily increasing, but positive. What about when your position is decreasing? As it is from t equals 2.45 to t equals 7. Well, all those slopes of tangent lines are going to be negative. So that's what it looks like on a velocity graph. We have negative values. And finally, what if you're neither increasing nor decreasing? What can we say about the position in that case? That's constant, unchanging, however you want to say it. But what does the velocity look like in those situations? So probably the easiest place to see this is between t equals 7 and t equals 8. We have a horizontal tangent line. What is a horizontal tangent line on a position graph? How does that get represented on a velocity graph? That gets represented as zeros. So tried to explain a lot of these ideas and a lot of these connections as clearly as I can. I am positive that many of you, if not all of you, still have questions. Please let me know what those questions are, and we can work on them together.